Welcome. Today we're going to talk about Taylor polynomials. Taylor polynomials are a very complicated subject. We're only going to scratch the surface. We're going to talk about the concept, come up with some formulas, we're going to do some examples, and we'll generally have some fun. So, what do we mean? A Taylor polynomial is an approximating polynomial. Imagine the black is your curve. It kind of does this, and it curves, and who knows what it does anywhere else. If you use a tangent line, you're approximating the function. We learned last time that a linear approximation is, or the local linearization, is the tangent line. And up close, the tangent line is actually really good. Look from there to there, or from here to there. It's actually pretty close. But what happens is the tangent line goes this way, and the function curves and goes a different way. So the tangent line is not perfect. It doesn't have any curvature in it, and that's important if you want to approximate better. So the next step beyond a tangent line would be a quadratic approximation. You can't call it a quadratic line since it's not a line, and you can't call it, well, quadratic tangent or anything because it's not a tangent. What do you call it? It's quadratic. It's a parabola that approximates. And hopefully you can see the next step would be a cubic. A cubic is going to be better still. Why? Because it has one more term that allows us some more flexibility in order to determine what's going on with the function. So, the green here is the parabola that helps approximate it. The red is a little bit better. Over here, the red and the green are not so great. They kind of both die off at the same place. But notice the red starts to take on a little more curvature there. A fourth order would look better than this. A fifth order still would look better. As you go on, each one gets better and better. Now, how close are they? These are the Taylor polynomials. And let's look at the Taylor polynomial formula. Here it is, drawn way far out. The Taylor polynomial, the first terms should look familiar. This one and this one are part of the local linearization, the tangent line. These two are the tangent line. If you want to go to a quadratic, go one more term. Notice this term. This term should be a little bit familiar if you looked at the local linearization video. Because there's the second derivative, there's the x minus a squared, there's the 1 over 2. What is that? That's the error-bound term. That's how far off you could have been in the maximum. So we're adding on the error to make it even better. Now, the next one on is going to look a lot like that. And if you don't know for sure what it is, you might guess it's going to be like 1/3 f triple prime x minus a. And you'd be almost right. It is f double triple prime and x minus a cubed. But there's not a 1/3 here. It's a 1/6. And the next one is 1/24. So what's going on here? Each of these terms is what's called n factorial. So this is 2 factorial, which is 2 times 1. This is 3 factorial, which is 3 times 2 times 1. And hopefully you can guess, this one's 4 factorial, which is 4 times 3 times 2 times 1. If you wanted to have a 5th order term, you would add on what? We'd add on 1 over 5 factorial, which is, do it, 5 times 4 times 3 times 2 times 1. What is that? It's 120. And then we'd have 5 primes. 5 primes is a little hard to write, so I'm going to use the other notation, parentheses 5 there. But this needs an A in here, by the way. That's a typo. Well, it's not typing, it's writing. It's a write-O. So, x minus a to the 5th. So you go on as many of those as you have n here. This n is how many terms you want to have. The highest power term, actually. Now, what's the error bound? The error is going to be less than or equal to 1 over the next term. So the tangent line, this was the error bound. So if I went to 5 of them, the error bound would be the 6th one. How do you write that in terms of n? You write n plus 1 factorial times the max of the absolute value of the n plus 1th derivative over the whole range times the absolute value of x minus a to the n plus 1. We won't dwell on that right now. We're mostly concerned with actually finding these Taylor polynomials. But the error bound is really related to it. Now notice it's not actually the same thing because there's an x here. It's the biggest this can be, not what it is at the base point. But let's talk about it. Let's do the 5th order one for cosine at a equals 0. And notice it says here, when a is 0, it's called the Maclaurin polynomial. Why is that? Because actually, Maclaurin and Taylor were students of the Newton field of calculus, the Newton branch of calculus. And so Maclaurin studied it first, and he said, I can approximate using 0. Then Taylor looked at this and said, I don't need 0. I can just do some other things, tweak it around, and generalize. So Maclaurin came first, and his are for a equals 0. And the Taylor's are any a. But their a is 0 here, so we're finding a Maclaurin polynomial for it. So I need the 5 derivatives here. Well, if f of x is the cosine of x, I'm going to have to find lots of derivatives. What's its derivative? It's minus the sine of x. What's the derivative of that? Minus the cosine of x. What's the derivative of that? That's going to be the sine of x. And what's the derivative of that? That's going to be the cosine. Now, hopefully you can get 1, 2, 3, 4, 5. What's the 5th derivative? Well, there's a pattern in here. It's going to be minus the sine of x. But we don't actually need these functions. We need the values at 0. So what is f of 0? Plug a 0 in for x, we get a 1. What's f prime at 0? Plug a 0 in, we get 0. A lot of these are going to be 0. Not all of them, but a lot of them are going to be 0 because the sine of 0 is 0. Every other term is 0 and it's going to disappear. It's going to be gone. These ones, 1, minus 1, 1, they're going to flip-flop. So we actually could come up with a pattern for a general one if we wanted. But look at this. What is each term? We get a 1. T5 of x is 1 plus 0 minus 1 over 2 times x minus 0 squared minus 0, or plus 0, plus 1 over 24 times x minus 0 to the 4th. Let me rewrite that a little bit simpler. So T5 of x is 1 minus 1/2 x squared plus 1 over 24 x to the 4th. This is a very good approximation for the cosine. Now, if you took this function, like the cosine, it's an approximation for it, subtract 1 and divide by x squared, you're going to have minus 1/2 plus something with x's in it. Let the x's go to 0. This can be used to find cosine limits. Likewise, you can use ones for sine to find sine limits. All the limits we learned for cosines in science can be approximated very well using Taylor polynomials. Let's try one more. Hopefully it's going to make a little bit of sense here. I'm only interested in the second Taylor polynomial here for a natural log of x over x. So let's try it. I need the function is ln x over x. Its derivative. Well, this is a quotient. So the quotient rule, derivative of the top times the bottom minus derivative of the bottom times the top, or the bottom squared. I get 1 minus ln x over x squared. The second derivative, this is getting a little bit booky. Derivative of the top times the bottom minus derivative of the bottom times the top all over the bottom squared. Now, it's important to remember we're plugging in 1. I don't actually need the formula, I just need what happens at 1. ln of 1 is 0. So the function is 0. F prime of 1. ln of 1 is 0, so I have 1 minus 0 over 1 squared, which is 1. The second derivative. Minus 1 times 1, so I have minus 1. Minus 2 times 1 minus 0 over 1 to the 4th, I get minus 3. Let's see, is that right? Yes, I think so. So, T2 of x is going to be the first one, 0, plus 1 for the slope times x minus the base value of 1, plus the second derivative with a half, 1/2 times minus 3 times x minus 1 squared. Let me rewrite that a little bit. I get x minus 1 minus 3/2 x minus 1 quantity squared. That's the second Taylor polynomial. Notice I don't multiply that out to simplify. I want it in terms of x minus 1s because 1 is our base. Hopefully, you can now do this. Try some out, see what it looks like. Until next time, this is Dr. Jet.